Thanks, Tony. So I'm going to talk about answering frequently asked questions in a bunch of these areas. This is mostly based on joint work with my colleague Hung at Buffalo and his student Mahmood and Chris at Stanford. And some of the stuff that I'm going to talk about also is joint with Dang Nguyen, who's at Logic Blocks, and Eli Parath, who's at Bar-Ilan. So in my house, the most frequently asked questions are what and why, by my son. But we're going to talk about more precisely mathematically defined problems. And I'm going to talk about a baby version of the general FAQs, and that's going to be the focus of my talk. All right, so here's the definition of the baby FAQ question. You're given n variables. So let's call them x0 to xn minus 1. So here's an example with 3 variables. And you have a hypergraph on these variables, and then you have hyperedges. So here's a simple triangle graph, and I'll call the edges R, S, and T. For each edge E in this hypergraph, I have a function, what I'll call factor, just following the nomenclature in probabilistic graphical models, that maps some stuff to some range. Okay. I'll also have a number f, which is between 0 and n, which corresponds to a number of what I call free variables. So this is the input. What you want to compute is essentially the sum of product. Okay. So you sum up over all bound variables, so variables that are not free. And for every edge in the hypergraph, you compute the corresponding factor value and multiply out of these value over all factors and sum it up. The addition and multiplication operator over this range script D will form a semi-ring. Okay. I want to mention that this baby FAQ was already explicitly defined much before our work. In fact, the earliest explicit work that we know is due to RG and McCullis. It's a very nice kind of a semi-survey paper from 2000. All right. So we call it FAQ because it also corresponds to functional aggregate queries. So you have a bunch of functions you want to aggregate together. All right. In case you're like me, before I started this work and you don't remember the definition of semirings because you saw it maybe in your discrete math class and forgot. So here's a quick kind of reminder. Not these kinds of semirings. So for example, the Boolean semiring, which the values are bit 0 and 1 and logical OR and AND. So essentially you want to do addition and multiplication, but you don't have subtraction and division. That's essentially it. You can also replace OR by addition and by multiplication, and you can replace 0, 1 by the set of complex numbers. So you get your usual, in fact, in this case it will be a field. So slightly more formally, the addition forms a commutative monad, so the addition is commutative, and it's closed under the values in this set D, and there's a special element 0, which is the additive identity. And similarly, you have a commutative monad for the multiplication, where 1 is the identity element. I've been putting a star across semirings because if I remember correctly, the traditional definition doesn't need the multiplication to be commutative, but we will in our case. Okay, and then multiplication distributes over addition, and 0 and highlights every other element when you multiply with it. Okay, so Anup had a question.
What is? Sorry, are the functions? Can you go back one slide? Are they Boolean functions?
Not necessarily. So they are on this range D.
Oh, okay. That's
so we are going to consider cases where the range are complex numbers. Though the Boolean case is going to be a very important case, as you might imagine. Right, so these functions can take values in D. So it turns out that these baby FAQs are very expressive, and in fact, the work of Ajay and McCullis, I think if I remember correctly, lists at least 10 or more problems that you can express as special instances of this sum product. So if you think about it for a bit, you can express constraint satisfaction or Boolean constraint satisfaction problems over the Boolean semirings. You can talk about probabilistic graphical models, in particular exact inference, if you know what it means, where the values are now positive numbers and you have the usual addition and multiplication. You can talk about logic too. I'm not sure if you can read it. The sign says honk, if and only if you love formal logic. And there's also a bunch of problems in databases, including the joins problem that you can express as a special case of this, and also a bunch of matrix operations, so in particular matrix vector multiplication. So in this talk, I'm going to focus mostly on the joins problem. if that name scares you, don't worry. I'm going to give a version that you would be very familiar with. And I'm going to talk about the matrix vector operation. So my plan in the rest of the talk is to first show you why these two are special cases of this baby FAQ, and then give you some algorithmic solutions to this. Okay.
Why is it called FAQ?
Because these are functional aggregate queries that are frequently asked in, yeah.
Why baby?
Just because I had a 3-month-old kid, so I could show the picture now. Baby is because the general version is more general than the version that I showed you. So our main results is we essentially have one single algorithm that will solve the general non-baby FAQ version, which I have not yet defined. Basically, it gives you one algorithm to rule all these pesky semirings at once. Okay. It turns out that these algorithms, when specialized to these special problems in some problems in probabilistic graphical models and logic, actually give you algorithms that run way faster than that were previously known. And for other problems like joins and matrix vector multiplication, they recover best known results. And again, I'm going to focus mostly on these two guys here. The technically challenging part is the analysis of the algorithms. In fact, our algorithms are not necessarily new. They're just simple twists on things that were already known. But I won't have time to talk about the analysis today. All right, so to Tony's question, why baby? So this is the baby version we talked about. Here's the grown-up version. What you allow in the so in the baby version, the sum operator over all the bound variables are the same. Whereas in the general version, the xi will have its own, can have its own operator plus. Okay. In particular, we allow this operator to be multiplication, or if it's not the multiplication operator, then this plus I and multiplication forms a semiring. But they're all semiring on the same set of values d. So that's kind of crucial. Any questions on the definition?
The multiplication is the same for all?
The multiplication is also the same for all. Yeah. Only the addition. Well, yeah, only the addition can change. All right, so the reason why this grown-up version is interesting, so it can handle things like quantified conjunctive formulas. So you can exist there all, and then you can also do count and stuff like that. So again, I won't go into the details. As I said, I'm going to focus more on the baby version today. All right, so I'm going to next talk about joins and this matrix operation and show you why they are special cases, contain special cases of this baby FAQ problems. So I'm not going to formally define the join problem. I'm going to give you a definition which should be probably more natural to this audience, but morally is the joins problem. So you're given a big hypergraph G. So let's say G is the graph of the internet, and you have a small hypergraph H. So say this is the triangle graph we had earlier. And the join problem essentially is you want to output all copies of H in G. Okay. Now there's technicality whether it's induced or not induced. Let's just not worry about that. So here's a simple way to encode this problem in this baby FAQ version. So this psi r corresponds to this edge r. For f x and y is 1, if x and y is an edge. And just to make sure they're not duplicates, you just say x is strictly less than y. Okay. And we are thinking of x and y as belonging to these set of vertices, and let's say we number them from say 1 to n or something.
Sorry, so do you blow up the vertices into a cloud with values?
No, so just map them 1 to 1, say from numbers from 1 to n.
So in picture below, you used to have an assignment to each vertex, right?
No, this is just a variable. Just a variable, yeah. And similarly, you define it for psi s and psi t. So if you just look at it from what this says is phi of x0, x1, and x2 is 1 if and only if x0, x1 is in R, x1, x2 is in S, and x0, x2 is in T. So phi of x0, x1, x2 is 1 if and only if it forms a triangle in the graph. So it's encoding the set of triangles. Okay. There is a question of how you encode the functions, and I'll come back to that in a bit, and that turns out to be a bit crucial. All right, so let me talk about matrix vector multiplication.
Sorry, what was it? So what do you get for the sum I understand this, but you have to now say something about the sum of products, right?
All right, so good point. So here I don't use the sum at all. I don't have to. So let me show you an example where I use a sum. But you're right, in this case, you don't need the sum. If you wanted to count the number of triangles, you could have just summed this over x0, x1, x2, and that will give you the number of triangles in the graph. All right, so let's do matrix vector multiplication. I'm assuming everyone here knows. So the way to think about the hypergraph is here you have just two variables. Now I'm just calling them x and y. The matrix corresponds to the edge, xy, and the vector corresponds to the self-loop, b. Okay? Now if you represent it as a FAQ, it's basically the form we have seen. So phi of x, you sum over y, which basically indexes all of these guys, phi a of xy times phi b of y. Okay? So again, in this case, I'm actually using both sum and product. It is known that in general you can't do this better than n squared, so there's a known lower bound. I'll come to this in a bit. Okay, so but we know we can do matrix vector multiplication faster for more structured matrices. In particular,
this thing is a number.
no, this is a function. So for every x in the domain, you get this value. So that basically corresponds to the xth value in the output. Yeah. So yeah, I'm always talking about functions and not. Is there another question? Right, so let's look at the discrete Fourier transform. Okay, before I go, how many of you have seen the non-recursive version of FFT before? Okay, so for those who have not, it was just as new. I just didn't know about this a few months back, so I'll show it to you. And in fact, our general algorithm specialized to the DFT results in this algorithm. Okay, so remember the discrete Fourier transform, we look at the x comma y entries, so think of x and y as numbers between 0 and n minus 1, is e raised to the 2 pi I times x times y divided by capital N. Okay. And I just want to show you the intuition behind the FFT. So let's assume n is some prime power raised to the 3. So this won't give you the ultimate n log n algorithm, but it will give you something quadratic, n raised to the 4/3. And there's an easy generalization to get n log n out of this. Okay, so we have this. What we're going to do is then express x and y in base p. Okay, so x0, x1, x2 are all numbers between 0 and p minus 1, and similarly for y. All right, good. So now let's multiply x with y. You just sum everything out, and you get this sum over j plus k between 0 and 4. You have xj times yk times p raised to the j plus k. Okay, now we'll substitute this sum over here, so you have sum in the exponent, so you take it out, you get a product. Okay, so again, the product is j plus k between 0 and 4, and you have xj, yk, and p raised to the j plus k. Okay. Now, the thing to note is, if j plus k is at least 3, this value is an integer, so I have e raised to the 2 pi I times an integer, so it's always going to be 1. So you can just drop them off from the product. Okay, so that's same as saying you only need to look at this product when j plus k is up at most 2. Okay? And this factor of 2 savings from 4 to 2 will basically make the runtime go down from trivial p to the 6 to the p to the 4. And I'll show later on, but that's essentially the idea. All right, so let me now just quickly go through essentially the motions to show why you can express this again as an instance of the baby FAQ. So we can represent this j plus k between 0 and 2 as currently as a bipartite graph. So you have x0 to x1 over here, y0 to y1, y2 over here, sorry, x0 to x2 over here. And they have an edge between j and k if j plus k is between 0 and 2. Because in particular, you don't have an edge over here. Okay. And then you also put in a hyperedge between all the y0 to y1. And here's how you do it. So phi b of y just get replaced by this phi b of y0, y1, y2. That's why you had this gray guy. And this axy is this product. So I've just replaced this guy over here, where psi jk is just this exponential. Okay, so I've re-expressed the DFT transform as an instance of this baby FAQ instance. Okay. Any questions so far? All right, so now we want to talk about algorithms for the baby FAQ instance. So what I'm going to do, instead of giving an algorithm for this entire general baby FAQ, I'm going to talk about algorithms for the two special cases, the joins case and the matrix vector multiplication. This guy is Mohammad Al-Khwarizmi, after whom the word algorithm is named. All right, so before even we go talk about algorithms, we have to figure out how the functions are represented, because the algorithm needs to know, say, the input representation as well as the output representation. The simplest thing to start off with would be to assume the truth table representation. So you just basically list all possible input tuples to a function and just store its value next to it. Okay? And just for the next few slides, for simplicity, I'm going to assume the domains of each variable is exactly the same. It's capital D. Okay? All right. So here's a very trivial algorithm that you can solve the baby FAQ problem. In fact, you can solve the more general version too. It's just essentially brute force. So go through all possible d to the capital N instantiations of x0 up to xn minus 1. Then substitute the values here, compute this value, and do this product, compute this for all x0 to xn minus 1, and then do the summation. Okay, so you just basically brute force everything, and you can do it in mn times d to the n. Does that make sense? Okay. So let's see what happens for matrix vector multiplication. D is capital N, and little n and m are 2. So in this case, you get the trivial order n squared algorithm. But this is optimal for the general matrix vector multiplication. Okay, so this trivial algorithm is optimal for the general matrix vector multiplication. Of course, since I'm calling it trivial, it's not going to be optimal for all problems. So if we try to run this on the discrete Fourier transform, D is P, N and M are 6, so you get P to the 6, which is again the n squared time. Okay, and of course, we want to do something better. All right, so we want to do something that's faster than the trivial algorithm. And those of you who have already seen the message passing version of FFT, this is what I'm going to talk about next. Though I'm going to state it in a slightly different way. Okay, so again, remember this is the version, the FFT version of the DFT problem that we want to solve. This is the corresponding hypergraph. And so what I'm going to do is start considering the y variables one at a time. So let's say, before I do that, I'm just rewritten the product in this form. I've dropped the exponent. So for example, psi 02 is same as psi 20 is same as psi 20 here, and psi b is psi b over here. Okay. So let's look at, say, the variable y2. It only participates in these two products. These two factors. So what that essentially means is all of the factors that are over here are independent of y2. So I can push the sum in. So this is an equivalent formulation. And now the idea is I'll compute this partial sum first. Okay, so it's sum over y2, psi 02 times psi b. So the idea is I'm going to use the trivial algorithm here again. So I just look at all x0. So all the variables that participate in this sum product is x0, y0, y1, y2. There are p to the 4 choices. I just go over all of them and do the trivial algorithm again. And I can compute this sum of product in time order p to the 4. Okay? And the idea is once I have done that, I can store this output in a truth table again and just plug it back in. Okay? So that's going to be a factor over x0, y0, and y1. Because remember, we are summing over y2. So we're essentially dropping y2 from the picture. Okay. So we can represent this as, say, phi prime x0, y0, and y1. So now let's look at the next y guy, which is y1. Okay. It participates in these three factors. Okay. And particularly the first three factors are now independent of y1. So again, push in the summation of y1. And again, I want to compute this sum product. Again, I'm going to use the trivial algorithm. The variables are x0, x1, y0, y1, again just 4 variables. So again, I can do this in time p to the 4. And then I'm again going to replace this by another factor, which will just depend on x0, x1, and y0. Okay. So this is where I'm at the end. I have this phi double prime and x0, x1, y0, and I have this summation over y0. And note that once I do this summation, I'm done. I'll get my phi x0, x1, x2. So you do So again, in this case, all the factors that remain you have to multiply. Again, use a trivial algorithm, p to the 4, you are done. So overall, it's p to the 4, which is n to the 4/3 in this case. And you can generalize this fairly easily to the general n case. So you think of, say, n as p to the m, where p is some constant prime, and then you just get, you'll have m such stages. Each will take time, roughly n, and then n times m, which m would be like log n in this case. Questions?
Can you capture Strasson's algorithm in this framework?
Not yet, but that's one of the things we thought about. Yeah. The thing with Strasson's algorithm, though, is it won't work over semi-rings because you need subtraction. So it is a very interesting question of what you can do if you add more power to your semi-rings, and yeah. By the way, this version, I said this has been known before. The specific version that I talked about was in RG's thesis. All right, so as you can imagine, the truth table representation doesn't give you much for too long. So here's another very natural representations, which is, let's look at this value psi e of x of e. If this value is 0, since 0 annihilates everything, you basically don't have to compute this product anymore. So the moment you get something which is 0, you know the product is going to be 0. Which means you only need to list the non-zero values of these factors. And that's only the interesting part of the thing. So that's how you represent the input, and that's how you want to represent the output. So we've already seen this a lot of times. So for example, for graphs, the adjacency matrix representation is the truth table representation, and the adjacency list is the listing representation. And in fact, there is a very big practical consumer of the listing representation. With databases, essentially everything is in the listing operation. Okay, so it's useful. So we want to talk about algorithms for this version. So now let's go back to the joins problem, and assuming now that all the factors are given to you in the listing representation, and the output also has to be in the listing representation. And let's try to run the previous algorithm that we were doing as before. So we'll pick one variable. Actually, it turns out it doesn't matter which one you pick now. By the way, we're going to assume that these factors are now of size n, which means they have all n, capital N, non-zero values. So let's take x2. It participates in these two factors. Now, in the worst case, you cannot prove anything better. So you have these three guys. You cannot prove anything better than n squared. You're stuck at n squared. Okay? And then you could say, well, maybe this is not so bad because maybe ultimately you have to spend n squared time, and so this is unavoidable. So the question is this time necessary? And another way to think about this question is to say, one way to argue that you would need n squared time is if you had to say that you had to, at some point, output n squared triangles. Okay, so if the worst case output size was n squared, then this time would perhaps be okay. Okay? So the question is, can you bound the output size? And one way to think about this is a three-dimensional thing. So you have axes corresponding to the three variables, and you have n values corresponding to CR over here, n values corresponding to S, n values corresponding to T, and you're asking how many three-dimensional points can you pack so that the projections are these three guys. So it was proved in the 40s that there are at most n to the 3/2 such guys. It follows as a special case of the Loomis-Whitney inequality. I couldn't find a picture of Loomis. So the question is, can you come up with an algorithmic version of the Loomis-Whitney inequality? So it turns out, even if you generalize the representations a bit and allow the factors to have different sizes, not necessarily all size n, but let's say psi r as size r, s as size s, and t as size t, then the Loomis-Whitney bound actually gives you square root of their product. Okay? So what I'm going to tell you next is actually a proof of this bound, but the proof will automatically suggest an algorithm to solve it in the same time, up to constant factors. Okay? So here's how I'm going to think about my factors. I'm going to have a column, so it's going to be a tripartite graph. Column for each of the variables, and for every value, every pair in psi r, I just have an edge between them. And similarly, pair that's in psi t, I'm going to have an edge over here, and similarly for psi s. And let's consider some fixed value C in the domain of X3. So I'm just trying to prove the Loomis-Whitney bound. So I just want to count the number of triangles that can be there. So I'll call, let's say, this red pill, blue pill algorithm. So you want to count the number of triangles that are here. So there are two choices. The number of triangles that C can participate in is at most the number of crossing edges on this side. Okay, so the number of triangles that C participates in cannot be more than R. Or you can also count the number of V's that go out from C. So if the degree of C on the S side is ds of C and the degree of C on T side is dt of C, then the product is also an upper bound on the number of triangles. And so obviously you can take the minimum of the two and get a valid upper bound of the number of triangles that involve C. Okay. So the point is you make this choice for every little c in C, and the runtime of the algorithm as well as an upper bound of the number of triangles is sum over C, min of these two quantities. Okay. Any questions so far? Okay. Oh, by the way, this algorithm actually is as old as me, so you can go back and figure out how old I am. But so essentially this algorithm first appeared in a work of Atri and Rudra. Okay. So let me analyze this algorithm. So this is the runtime. Again, I have to constant factors. There are certain things you have to do, like have the correct hashes in place and things like that, but they're all fairly simple to do. So we want to analyze this guy. So sum of minimum of two quantities. Now we observe that minimum of two non-zero guys is at most the square root of their product. So you write it like this. So you have the sum, then note that this quantity R is independent of C. Bring it outside. You have sum of products. You have to use Cauchy-Schwarz. There's nothing else you can use. So you apply Cauchy-Schwarz, bring the summation inside the square root. So now you have sum over C of the degree of C in the S guy, square root of that. So this sum is exactly the size of S. This sum is exactly the size of T. So you get square root of R times S times T. So you both prove the bound as well. And again, the runtime of the algorithm is within constant factors. Questions?
Does it lose by some factor 2 or something?
For the case when R, S, and T are different size, it can actually be unboundedly far away from the actual answer. So there's an LP-based bound which is known to be tight.
So I guess a lot of times, I mean, I've seen the proof of this through Shearer's lemma.
Yes. Yeah.
So can you ask to make like all bounds which follow from Shearer? You know,
So our general result basically argues this for any joint query. So for any subgraph, any fixed subgraph that you want to list, we can get the optimal algorithm in the runtime, which is linear in the version.
by Shearer or something.
Yes, or this version, but yeah.
And does it always use just like Cauchy-Schwarz to prove these?
Holders for the general.
Holder, okay.
The original proof is Holder.
Holder. The original proof is Holder. Yeah.
I didn't realize that. Because also
Yeah.
it seems to be connected to like, you know, quasi-regularity, you know, like counting 4 cycles to this. Oh, yeah.
Yeah. So the original proof is not decided. It follows from Holder. Yeah.
Yeah, quasi-random. Yeah.
All right. So let me just speak. I'm almost trying to turn. I'll be quick. So the general algorithm for the general FAQ essentially combines the two algorithms we have seen. So you start out run the quote-unquote the trivial algorithm, which is again the simple generalization of the algorithm we saw for FFT. And remember, at each point we were computing this sub-problem. Okay? Instead of using the trivial algorithm to compute the sub-problem, use a suitable generalization of the algorithm we saw to the joint problem. And that's essentially the algorithm. And again, this framework is not new. At least in the work of Grohan and Marx from 2006, it's been around. So in some sense, the thing that I didn't mention was the FFT algorithm worked correctly because I showed you the correct order of eliminating the vertices. If you use the wrong order, you won't get the n log n time. So in some sense, the only ingenuity in design the algorithm would be to compute the quote-unquote the correct variable ordering. So that's essentially the only problem that you need to solve. The rest of it is kind of trivial. So I just want to point out the algorithm is simple. So we have actually implemented this algorithm. For example, listing or counting the subgraphs, there are many engines, for example, from Oracle, from GraphLab, which I guess is now Dato, and there's also systems from Logic Blocks and Snap at Stanford. So Chris and his colleagues implemented this. And so this is Chris again and Andres, they're the student lead authors. And they basically beat the existing systems by 10x, at least. So some of the systems we're beating by 100x. Okay, so if you want to read further on this, if you want to talk about the result that to answer Anku's question, we have a worst case optimal John algorithm for all hypergraphs. This appeared in PODS 12, so one would think that that would be the best paper to read up, and one would be wrong, so please do not read the PODS 12 version. There's a 20-page proof we reduced to 2 pages, so this is a survey that we wrote which has a better proof. Okay. We also were able to show that bunch of John problems with some new algorithms for Johns have very strong connections to resolution. And these give beyond worst case analysis guarantees for John algorithms. And again, this is the paper to look at. These algorithms, again, turn out to work really well in practice. So we can't beat all systems, but we can beat many systems, again, by factors of 10x and stuff. And if you wanted to know more about the FAQs, this is the version. There.
Questions? Time for a couple. So I have a question about the variable ordering. How do you do that? And it's a hard computation.
It's a hard computation problem. So to compute, for example, the correct tree width bound, which is what you would need for the trivial thing, is NP hard. We don't even know a constant factor approximation.